Okay, welcome to another riveting week of IGM202. Today we're going to talk about one of my favorite subjects, which is collision detection. You may be like, why is that so exciting to you? And I won't have a good answer. But it's one of my favorite subjects in game development in general. And we're going to be kind of exploring it for the first time, and you guys are going to be using it for some of your assignments and projects coming up very soon, if not now. So let's dive in. So what is a collision? And this is brought to you by zombies. Cute ones. I decided to keep the various clip art and fun things in this lecture because I like them. So yeah. So what is a collision? Basically, it's when two things collide. I think that's pretty clear. Effectively, in a video game or in any kind of application that's real time, that's updating itself, you want to detect when certain states occur. In a traditional piece of software, states occur because of user input, because of changes to the data, what have you. And in that context, a video game is very similar in that you may have two objects that are behaving independently and may come into contact in some way. And you want to detect that contact so that you can react to it, or that the objects can react to one another. And so collisions are really the way that you can start doing things in games, unless you want to do some very like Sudoku type of game where there is no collisions, but for the most part, any kind of, almost every single kind of application, even traditional software like a Sudoku puzzle, you need to detect when the user clicks on a particular box. And that is a collision detection algorithm that we'll be talking about here. So this set of techniques is actually super general in the way that you can use it. And honestly is to me one of the most exciting things and funnest things to play with. So effectively, a collision is when two or more objects intersect. This event is detected by the code, by the programmer. And then generally, as you've already seen in Unity, most engines have some kind of collision detection helpers, for example, the collider in Unity. And there's a variety of different types of intersection and or collider geometry options. These are just a few, and we'll talk about a few more in the rest of this lecture. But for example, two boxes overlapping, or a box in a circle, and a circle in a circle. Now we're talking about 2D in this case, but these algorithms do generalize to 3D as well. So just keep that in mind. So a couple of really basic 2D testing approaches is what's called bounding boxes. So two boxes overlapping with each other. Bounding circles. So imagine an object encapsulated by a circle. And also point to shape. And we're going to go through each one of these and talk about a few more. There are others. You'll actually see a hint of the separating axis theorem in this lecture. Although the separating axis theorem is a much more general approach to detecting collisions with arbitrary axes, with arbitrary shapes, and there's a lot more in that. There's pixel perfect collisions. These can be extremely computationally intensive, so you can explore that on your own if you're interested, or bring that up in office hours. There's also the optimization of collision detection. So imagine if you have two objects and they're colliding, that's not so hard, but what if you have a million objects? How do you deal with that, right? Because if you were to check every object against every other object every second, or every a particular number of times a second, very quickly you're getting into the billions of calculations per second, and these detection tests and these intersections techniques are not cheap. They tend to be computationally intensive. So this is one of the reasons that I love this subject so much, is that it's very easy to understand at sort of the basic level, and you can get some really cool stuff happening day one, but it goes super deep. In fact, this is I would say still an active area of study and research, is how to make better collision detection algorithms, how to make them more optimal, to make them more general, to make them faster, and all that. So it's really kind of a cool area to explore. So let's talk about Unity and sprites. We've got a couple of helpers in Unity, and we're going to kind of talk about the algorithms behind two of these collision detection techniques. So what we need from our sprites is we need the minimum x and y coordinates. We need the maximum x and y coordinates. So there's a couple of ways to do this. You either hold the max y, max x, and min y, min x, or you can also approach it with knowing the center and then what's called the half vector, which I'll talk a little bit about in a later part of this lecture, but either one works. If you're using a circle, you need to know the circle radius, so in that case you do have the center, and then you draw a circle around your object such that every part of your object is inside. And also you need to have the distances between objects. That's all the information that you need to detect a collision. So the sprite renderer component has this read-only bounds property. If you're writing your own engine, you'd have to develop that, but Unity provides that with you, so you can have the center, you can have your minimum, you have your maximum, the size, and the extents. The extents is that half vector I was mentioning before. As you can see below here with this sprite, the center is at 0, our maximum is 100 by 160, our minimum is -100 and -60, our size is 200 by 120, and as you can see the extents is the half of the size, which is 160. And you can sort of see some of this data, some of this information is sort of superfluous or redundant in that if you know the center and you know the extents, you can actually get everything else from just those two values. But sometimes it's really convenient to have all of those available to you. In this context, we've got a sprite positioned at 0 with a width of 200 and a height of 120. So even, that also is a way to have that information. There's a lot of different ways to get to this information, but ultimately you're getting to the same thing. So to in your own scripts, it's helpful to use the bounds property, but it's not required, right? For example, a bounding box script has the reference to the center, to the width, to the height, min and max y, min and max x, or kind of a bounding circle script that has the center and the radius. If you specify the width and the height or the radius, you don't rely on the bounds of the sprite. And the benefit to this is that you have a little bit more control over the shape. So if you're limited by, if you're using the script, if you're using Unity's built-in properties, you can't change them because it's read-only. So if you set your own, then you can say, oh, actually, I want this object to have a smaller bounding box, or I want this object to have a bigger bounding box. Maybe, for example, you have an object, but you want to know when it gets close to something. That's one reason to do that. Or another reason, as we'll see in this slide, in this lecture, is sometimes you want an object that's bigger because the things that it's interacting with may be moving very quickly. You want to make that test much larger, and then to detect an early detection of, say, you're shooting something with a very high velocity bullet. So you make the bounding box extremely large to detect that event, and then you run more code to detect the explicit, did it actually hit and where and whatever, which might be a more expensive operation because we'll talk about that in a second. So this is kind of an important thing. The bounds is in world space, whether or not a sprite is a parent or a child. Now, this is really important because so I've written a lot of these engines. When you're doing collision detection, you want to be in absolute or world space. Otherwise, it's really difficult to kind of figure out where you are. So oftentimes, this is important because if you're trying to use your bounds respective to your parent, you might not have the correct information. So just be aware of that. That if your sprite is the parent, great, like the information will be the same. But if your sprite is a child of something, then the center and will actually be relative to the sprite, not to the parent. So just be aware of that. The math kind of doesn't care ultimately which one you use, but you should care. So be aware that it's different. Scaling also affects the calculations. Ultimately, if you have a object with a 50% scale, then all the numbers just get smaller, right? The bounding box gets smaller by 50%. Its position does not get smaller. The position stays the same unless your scaling is at the parent object. So you can kind of hear like these things start to get really nested. As things get more nested and more compositionally complex, it's a little bit harder to keep track of what's happening where and whatever. So keeping an absolute values is really valuable. But if you scale something, your bounding box is scaling too, to kind of be exemplified in a bit. So another thing you kind of have to think about is your camera size. The size of the camera in the context of the sprite system that you're using will affect your math. So again, this is a bit more of a nitpicky Unity thing. So just keep in mind that your camera and the width and the sizing of your camera needs to be the set to a reasonable PPU or pixels per unit. And that way your data might work. So like what you want to do is you want to set your camera size to something like 500 so that it can scale it scales by 100 or is divisible by 100. And then you can set your aspect ratio in the game view, which will allow you to be able to actually predict the numbers in your math. So if you were building an engine from scratch, you would have all this stuff built in, and when Unity does this stuff under the covers, it doesn't have to think. This is all built into it as well. It's pulling data from all the various sources that it needs to pull to figure this stuff out. But when you're doing it, just keep in mind you do have to define your sizes of everything. Otherwise, your numbers may start to come out kind of funky because you're going to be operating on Unity units, but you might be converting it into pixels and so on. So just keep in mind that your camera settings will come into play and be aware of that. So, okay, let's get into the algorithms. Fun stuff. So let's talk about our first algorithm, which is the AABB, Axis Aligned Bounding Box. All the algorithms we're going to be talking about are going to be in 2D. However, I should note that all of this does generalize to 3D. So the idea with an axis-aligned bounding box is actually pretty straightforward. You take your object and you draw a box around it. So imagine a zombie, like the one to the bottom left, and we look at the maximum point away from 0 and the maximum point away from negative in the opposite direction. And then you it's almost like you're just doing a maximum point, both in x and in y, and that value becomes a vector, and you use that to draw a square. Like take the vector and you in opposite directions and you draw a square. So actually determining these bounding boxes is pretty easy, given that they don't change for a given sprite unless your sprite's changing. That's a different subject. But for the most part, once you set it and forget it. And so the reason AABBs are so powerful is that by way of being aligned to the axes, the math becomes really, really simple to kind of figure out if things are overlapping. You can probably already think right now how we would test whether two boxes are overlapping. And this tends to be a really simple a thing to kind of figure out early on, and we'll talk about that. So let's talk a little bit about the sizing. So obviously I said your minimum bounding box needs to be what's your maximum point and whatever, but you can also do whatever you want, or you can make the box wider and taller than the actual object. And you can kind of think about what are the benefits, right, to this. Like in this case, there's a downside. If our boxes are too wide, right, we have some white space. This collision looks like a collision, but to the code, but it's not actually colliding yet. So being too big, you have these false positives. But if you make it too small, right, if you make it smaller, now you have the situation that does represent better. You can get less false positives. However, you can see here in this right picture, the zombie's hands are sticking out of the front. So if this flower guy was taller, or say the zombie was walking into a wall, those hands may be going into the wall before the collision system detects that there's a collision. So we have these false positives. When you have a bounding box, you have to kind of take into consideration the amount of space where you're going to have false positives. And that's going to be, the area that there actually is no object in this thing. However, if you make your box smaller, you're going to have a lot of false negatives as well, where there may be a collision. And actually, the right picture here does demonstrate a sort of approach to dealing with this, where instead of one bounding box, you can represent an object with multiple bounding boxes. And a really fun trick in this is you can actually composite these. I'm not going to talk about this in this lecture, but if you guys want to try this, here's a above and beyond thing for you guys who are always asking what are some options. Above and beyond here is, what if you could nest bounding boxes? What if you could have a box, and inside of that smaller boxes that represent the geometry of a sprite more accurately? You can see that even with a really simplistic algorithm like an AABB, you can get extremely accurate collision results, and that are performant, because what you're doing is you're testing the big bounding box, and then, okay, maybe we have a collision, then you keep on testing lower and lower until you confirm, yes, there's a collision for sure. And actually, this is a pattern in collision detection, which is exit early. You want to exit as soon as you possibly know that there's no collision. So, for example, often you'll find collision systems that use all of these bounding hierarchies, where you start off with a sphere, which is the cheapest, you get down to an AABB, then you get down to more and more discrete, and all the way down in case that you really want to know, oh, this is actually hit. So for example, in like a first-person shooter, you want to be almost pixel perfect just because of the accuracy demanded by a user, and people don't actually shoot the gun that often by comparison to like running around and walking on the ground, which is all the time. So there's no real right choice here. Again, this is up to you as a designer, as you as a developer. You can get super intense and crazy. You can also just be like, you know what, whatever, I don't really care. The gameplay is going to be more about other things than collisions and stuff. So it's up to you. You get to decide how well these things work, because there's a trade-off on the other side. The more collisions, the more discrete, the more accurate the representation is, the higher the performance cost, and you may be contending with other stuff like graphics and physics and so on, right? So collision detection actually is not the physics engine, and you do need to kind of keep that in mind, that physics and collisions are two different subjects practically, although they obviously work together. So this is obviously an online class. You're not going to break into smaller groups. I recommend you take a minute right now, you pause the video, and kind of think about, how would you determine if two boxes are aligned bounding boxes are intersecting, and kind of write out the pseudocode. This should be pretty straightforward given the simplicity of the system, right? You can probably imagine how you would have two boxes overlapping. So I'll let you guys pause the video now if you'd like, or don't, and then watch me explain it anyways. Cool. So Let's talk a little bit about the bounding box and what it looks like. You've got the maximum y, you've got the minimum y, you've got the maximum x, and you've got the minimum x, and we are guaranteed that this box is aligned to the axes. That's by definition. So what we want to do, first let's look at the x-axis. If we are overlapping in x, meaning the maximum x of box A is more than the minimum x of box B, then we have a potential collision. You can imagine if the two of them are above each other, you can have an overlap in one axis but not the other, and that would not be a collision. But now we have at least knowledge, okay, there may be a collision here. Again, similarly, if we have kind of the opposite, if box A is on the right and box B is on the left, we can do max x of B and min x of A. So again, we're looking at this overlap. Is there an overlap? Now we can look at the y-axis, and we can see here that max y is greater than the minimum y of A. So really what you're trying to do here is it's just a min-max calculation of these points and looking. And if both the x and the y are overlapping, then you've got a collision. Similarly, if you flip the boxes here, if your max y is greater than your min y of B, you've got a potential collision. So this is exactly what we do every single frame. We check the minimum x of B, is it less than the max x of A? We check that the max x of B is greater than the min x of A, max x of Y, min x of B. You get it. It's pretty straightforward. You want to kind of do these two and figure them out. So there's another way, and this is a bonus way. I added this to the materials because I think that this is a little bit more eloquent and does kind of hint at future applications of this. So there's a slightly more eloquent way to do this, and it's up to you if you want to try it or not. Effectively, we can actually do this check in just a few lines of code. And you can kind of see here where we have the half width of box B and the half width of box A, and we have their centers. And if we take the difference between the center of B and A, we get this distance. We get a vector, effectively. The vector has both an x component and a y component. And if we take the absolute value of that, we've got a value. We've got a sort of distance between the boxes in x and a distance between the boxes in y. And you can kind of see where I'm going with this. If you take the value, the half width of box B and the half width of box A, and you add them, you're going to have the maximum distance between the two boxes that you can have with them still touching, right? Imagine if you took box B, you took box A, and you put them right up against each other. They're going to have a distance between the centers that's equal to the width, half of the width of B plus half of the width of A, right? Every time. So if the distance between those two center points is more than that distance, then it's not touching. And so that's all we have to do. We check, is the distance between the centers more than the maximum distance where we know it's not touching anymore? In this case, we see there's a small overlap, and you can see in the bottom here, I drew the half width of the two boxes sort of overlapping in a way where you can see there's a small overlap. And that overlap indicates to us that there's a collision on the x-axis. On the right side, you can see the same thing done for the y-axis, and so the exact idea, imagine stacking the two boxes on each other. There's a distance in y of the two centers, and that's going to be equal to half the height plus half the height of the other. And so we kind of stack them on top of each other, and we see on the right, when we line them up, we can see, wow, there's actually a almost perfect overlap there of the two, because you can see that the box A, the top of it, is almost perfectly lined up with the center of B. And so what we're doing is actually we're doing a elimination test. Are the centers spaced far enough apart that they're no longer touching, or are they spaced enough far enough on top up and vertically that they're no longer touching. If either one is true, if either condition is true, we return false and we get the hell out of there, right? Otherwise, we must be touching. So let's take a look at sort of the negative situation. In this case, you can see the y-axis is overlapping, but the x-axis is not. And what that means is that we're going to hit that first conditional, and that's going to escape. We're going to say, oh, there's no way. And this is actually a very simple version of the separation axis theorem we talked about earlier on in the lecture. You can actually see it's, oop, wrong way. Whoop, oh, I can't escape it. I can't escape the camera. There it is. Anyways, oh no, can I get back up? Yes, I can. All right. Whew. So you can kind of see the separation axis theorem is really simple. It gets a little bit more complicated, but ultimately all you're trying to do is you're trying to see, can I draw an axis? Can I draw a line that separates the two? And what you're doing is you're taking a particular dimension of the object and projecting it down onto an axis, in this case the x or the y axis. And then you're doing this very simple test, this overlap test. And if you can ever fail the test, as we did here, then they're not touching. So the separation axis theorem is simply a test by elimination. And you draw these axes. In the case of a bounding box that's oriented by the axes, there's only two axes. There's the x and y. You don't need to test anything else. If you cannot find an axis that separates on x or on y, then they're touching. So you can see this code is a little bit simpler and a little bit more eloquent than before, but requires a little bit of a deeper understanding. So again, this is more of a bonus edition. I thought this would provide a little bit more context and a little bit more sort of depth of info. So hopefully that helps you guys out a little bit. Great. So let's talk a little bit about the pros and cons. So one of the pros, super fast, easy to implement. It's not that CPU intensive. So this is quite good, especially for objects that are not going to rotate, they're axis aligned. But the disadvantage is that whenever the object moves, it's not entirely true. You don't have to recalculate the bounding box when the object moves, but you do have to recalculate it when it rotates. Now it's true you have to recalculate the minimum and maximum x whenever it moves. That is true, but if you use that previous example of the half vector, the extents, and the center, you won't have to recalculate them because you're always going to have your location, and you just kind of add to your location your half vector, and then you have your values. But it's true, the way that you architect this code does come into play in terms of how efficient it is when objects do move around. And if things rotate, this doesn't actually account for that. And while there are simple ways to deal with it, there are, the simple kind of approach to it doesn't actually account for any kind of rotation. This also will have a really tough time with concave objects. What's a concave object? Like imagine the letter C, right? There's a big empty concave, like a cavity inside of it. And so the entire cavity will be considered a collision if you're just drawing a box around the letter C. Now you can do things like we were talking about where you can kind of create multiple bounding boxes, but generally speaking, concave objects, for collision detection for concave objects, is one of the hardest things to deal with. And usually what you do is you either break it down into simpler non-concave objects, or you do a per triangle or per or pixel perfect calculation, which is very, very computationally intensive. So AABBs, I wouldn't so much say that that's a disadvantage. It doesn't work with it's a feature, not a bug. It's not supposed to work with concave objects, but to get it to work with concave objects, you do need to do a lot more work. So you do have to be aware of that. You may have really bad results if, say, you have say like a archway and you want to do a collision with an archway. You got this big empty spot in the bottom that the collisions are not correct. So let's talk a little bit about bounding circles. The ordering of this is kind of funky in that bounding circles or bounding spheres are actually the simplest and most computationally cheap approach to doing collision detection. So really all you're doing is you're taking a object and you're taking its center and you're taking from that center a radius and you're drawing a circle. And that radius is actually the same half vector as the bounding box. So you can imagine you try to find the place in your object that is farthest away from your circle, from your center, and then you draw a line where it encompasses the entire object. And so it's a bit complicated in that you have to sort of make sure your object is in the center. You might have situations where the farthest point, now you have this kind of empty space, so you can sort of figure out, oh, well, I want to figure out my maximum and my minimum point, and you draw a line, you find the midpoint, and then that half the length of that line is your radius. And what's really nice about bounding circles is if you rotate the object, if you set everything correctly, that is, rotations do work. So this is really good. For example, a billiard game, you can do everything with bounding circles, and awesome, the cost of doing it from a performance standpoint is really, really low. So yeah, it's a really great way to do non-axis aligned collisions that rotate. The circle size does come into play. We talked about how do you get the minimum circle. If you have a smaller circle, you can, again, just like with the bigger or smaller box, you can sort of create different effects. So in this case, for example, we've got a situation where these two zombies are colliding, but you can see there's a lot of space between them, whereas on the right example, they're touching each other, but that collision has not been registered because the bounding circles have been set to too small. So you can kind of see bounding circles are not terrific for objects that are rectangular in nature, but they can work. And they can also work as an early detection test. So say you have 1,000 objects, you can use circles to detect, is there a chance that these two are touching? And that way you're only doing a circle test for thousands of objects. And only when the two are actually touching with a circle do you do the lower level test like an AABB or something more sophisticated or like a pixel perfect test. So you can see, again, going back to that nesting idea, which again is not going to be required here, it's just I'm trying to provide a bit of context to how else you might use these in the larger system. So we were talking about this earlier, right? We can create a lot more accuracy by creating multiple levels of bounding circles, and actually circles are really easy to do this with. As you can see, circles tend to do a pretty good job of kind of providing a max coverage of the geometry. Like on the right side, you can see very little. There's very little waste. There's very little white area, and there's actually a couple of examples of collision regions that are not covered. Like if you look at the zombies' hands, as you go to the left, there's a small little section, kind of on the upper arm, that's not covered by any one of the red circles. However, they're surrounded by red circles, and that means that a collision has to take place for something to end up there. There's a very low likelihood that we're not going to get a collision in that area. So it's pretty effective to create this compositional, this hierarchy of circles. So again, take a minute, pause the video, think about how would you determine the overlapping of bounding circles. I'm not sure why it says bounding boxes, but you know, we're talking about circles here, so how would you determine the overlapping of two circles? And I will add, there's a bit of a hint I gave you in the previous example. So pause the video now, or don't, and watch me talk about it. So to detect the collisions, we actually just have to look at the radius of the circle and the positions, the center of the circle. That's all the information that we need, is the center and the radius of the respective circles. So just like we did in that second example of the bounding box, the axis-aligned bounding boxes, what we do is we can take the two positions and calculate the distance between them. In fact, we don't even need to know much about anything else but the point A minus point B and the magnitude of that, right? Point A minus point B is going to be a vector. You take the magnitude of that vector, and now you've got a distance between those 2 points. And if you can imagine two balls touching each other, right? The minimum distance between the two centers is going to be equal to the sum of the first radius plus the second radius. So if the two centers are if the distance between the two centers of the circles is anything less than the radius of those two, of the sum of the two radiuses, then they're touching. If it's more, then they're not touching. And again, this is just like that axis-aligned thing, except with a circle, the axis of the axis of the separation, there are infinite axes of separation. Infinite, right? Like, I can take a point on any part of the circle, I can draw a tangent, and if I can find a point, a line that separates them. And so in that sense, it kind of breaks down to the fact that you can project these things onto any axis, which means it's just the magnitude of the 2 points. If that's more than the radius, then you're done. It's that simple. For example, here you've got this example. It's not well represented because that line, you don't want to project it down to the x. Actually, what you want to do is you want to draw a line between the two, and you'll see that the two are touching one another. So yeah, so all you really need to know is you need to find the distance between the two. To do that, you're just finding the magnitude of a vector, which as you can also, which is basically just the x of 1 minus the x of 2 to the power 2 plus the x of 1, the y of 1 minus the y of 2 to the power 2 is equal now to the squared distance. If you take the square root, then you get the distance. However, I will say this. Operating on the square sometimes is better. So if you take the difference of the 2 points and then you square each one, so x1 minus x2 to the power 2 plus y1 minus y2 to the power 2. Now you've got the distance squared. And if you take the radius, the sum of the radiuses, and you square that, now you can just compare that. Like, you don't need to do the square root. And the reason that that's important is that square roots are expensive on computers. And if you're doing this calculation many, many times per second, you can save a lot of cycles by operating on the square. It's much easier for a computer to multiply two numbers together than to take the square root of a number. And so if you're just operating on the distance squared, you can save a lot of compute time. So some advantages: there don't need to be axis aligned, the rotations work, the algorithm's super simple, there's nothing simpler practically, and you can be a lot more accurate for certain shapes, like a concave or a circular thing, where it's really hard to represent a circular object with a box. And obviously, as you saw, we have a lot less loss with a concave, where you have the C, you can cover the C, and then you can even have a anti-collision inside. So imagine like a C shape, you have one bounding box on the outside, and then you have another bounding box on the inside that is a rejection box. So if it collides over the big box, but it hits the small box, then that's not a collision. So you can kind of do anti-boxes too, which is important to note. You can really composite these things in very intricate ways. So the disadvantages: it can be more CPU intensive if you use the square root. However, as I mentioned, you can actually nix out this disadvantage by not using the square root at all. You can just do the sum of the squares, and using that. And obviously, if you're trying to represent rectangular data, the circles won't work quite as well. So to talk a little bit about some other detection methods. What's called a point to shape. This is similar to the box and circular. You're going to be thinking about this for things like bullets, and you can apply basically a point collision to a axis aligned bounding box or a point to a bounding circle. And with a bounding box, it's quite simple. The point, you're just checking the bounds, just like we're doing max and min. Well, now you're just doing, is this point less than the max x, more than the min x, and same thing for y. And for the bounding circle, it's even easier where you take the distance of the point to the circle point, the circle center, and is that magnitude difference smaller than the radius? It's similar to, by the way, two circles colliding, but one of the circles has a radius of 0. So it's actually the same algorithm as that. And by the way, that's a hint for how you were to do axis-aligned bounding boxes and points and circles. You can use some similar tricks. So in this case, right, we can see the dot is in the bounding box. We're less than the maximum x. We're more than the minimum y, x. We're more than the minimum y. We're less than the minimum maximum y. And in the same case here with the circle, in the dot is inside of the circle, because if you draw a line from the center of that circle to the dot, that magnitude, that distance is going to be less than the radius of that larger circle. So pretty easy to check. So talk a little bit about some of the other checks, and this is just for fun. Like this, if you want to do some of these, great. But really, this is just because I enjoy the subject. You've got a array. Array is actually really important to talk about in that array is like a point with a vector. So you have a point and a direction. And this is actually really valuable. So imagine a bullet. A bullet can be moving really fast. So if you're checking the actual collision all the time, you may have trouble with that because the dot might be moving really quickly. You might miss the collision window, a lot of things like that. Sometimes you want to have array. An array is really good for things like object selection. So say I have my mouse and I want to select an object in the scene. So you ever wondered how Unity knows which object you're clicking on? It uses array to cast into the scene. If you're familiar with ray tracing, right, the ray intersection actually is a very, very well understood topic and is very valuable to kind of understand as well. So how would you intersect array with an axis-aligned bounding box? This one's actually pretty simple in that you are kind of looking at the bounding box as a set of axes, and you want to find the minimum x intersection of the left side of the box, the minimum and the maximum x. You kind of see these 2 points. The same thing for y. You can kind of figure out whether or not the ray is actually hitting the box. It's actually a really simple algorithm to figure out and can be very powerful. Similarly, a ray and a circle. This one's a little bit harder to figure out. You have to do a little bit of geometry to kind of understand how do you determine what those points are and whether or not it's touching. But a ray and a circle is very powerful as well. Now, you've got the axis-aligned bounding box and the circle collision. This is a really fun one, and there's an algorithm called Avro's algorithm that I recommend you guys check out if you're interested in that. You can do some pretty fun checks and figure out the collision. And then this is pretty powerful in that, you know, when you take a box and an axis-aligned bounding box, a circle and a bounding box, when a ball hits it in a particular way, you can have some really cool dynamic and interesting behaviors, especially if you're doing physics. And then finally, the oriented bounding box, or what's called an OBB, and a circle. Obviously, OBB and OBB gets pretty complicated, but an OBB and a circle, if you can do the axis-aligned version, what you can do is you can actually transform the entire system to make the OBB and ABB, and then you're doing just the AABB and circle collision detection calculation. So These are all within range of you guys being able to do them for this class if you want, but just kind of explaining, there's a lot more, right? There's everything, right? Everything from just an arbitrary mesh to another arbitrary mesh and things like that. So collision detection, really fun subject. So some considerations. We've already talked about this a little bit, but when you have an object that's moving and you want to detect its collision, you can have a situation where the object that you're trying to detect the collision of is moving so fast that the time that you test the collision initially, t0, you're not going to have a collision because it's over here and your object is here. But then the object is moving so quickly, so the next time you check your calculation, your collision, the object is here. And even though technically it passed through, given the velocity of the object, you're not going to detect that collision. It's going to go through it. And you can miss that. And so you have to be mindful of the speed. And in this case, again, you can actually leverage something like the ray intersection test to determine, okay, this object moved really quickly, but is there a chance that it actually passed through? What was the previous point and what's the current point? Can we draw a ray? Is there a chance that it collided during that time? And then you can kind of do a post detection, like, oh, it collided here, and it's going to bounce that way, whatever. There's a lot of different approaches to solving this problem, but you do have to be mindful that if you test the collision with a time step where objects may actually miss but by going through, because the calculation is not going to have a chance to hit at a time that actually qualifies for collision based on our math. So we talked a little bit about this already. The more collision detection you have, the more processing power you need, right? So if you have a system of, say, a bunch of billiard balls, you want to test each ball against the other ball, and that can, it scales up exponentially, so you have to be aware of that. And how do you optimize it? Well, you can sort of choose the proper detection method, so use the best one, or, as I was mentioning, use a simple one and then go down the stack to do the more accurate one. So you start off with something that's not so accurate, but is cheap, and then you only check the collisions of things that or have a much higher likelihood of colliding. For example, just a very simple thing is like, don't check the collisions of things that are far away from each other. That's a very simple approach. The other thing we talked about already, don't do the square root, just compare the squares. You can do this for the circles, and there's going to be a lot of other situations where you might be able to apply this. Obviously, you can check less things. That's up to you. And then finally, there's the whole subject of spatial partitioning. So I already talked about don't check two things that are too far away from each other to potentially collide. And you can generalize this into creating a data structure that has sort of an organization to it, where the organization of that data structure is representative of the spatial organization of the objects. So that way, say you have a binary space partitioning tree, right? You know that, say right here is the center, and objects here have zero chance of interacting with objects here. So you've now, just by virtue of that, cut the number of checks in half. And you can keep on cutting it in half, and so you can get to a point where only the objects that are likely to be touching are represented by this binary tree. But this can get pretty expensive sometimes too if these objects are moving and then your tree's changing and so on. So be aware everything has benefits and trade-offs. So we've talked about just collision detection up until this point. And collision detection is when two things are touching, but you don't know how they're touching. You just know that they're touching. You don't know where, you don't know why, you just know that they're touching. And sometimes that's enough, but oftentimes you want to handle that, or you want to know how they're touching. Now, we're not going to talk about collision resolution to a very high degree in this class, but collision resolution, just to quickly talk about it, can go as deep as figuring out, oh, two objects are touching, and this is the point of contact, this is how far into each other they're touching, this is the normals at the point that they're touching, and you need all that information to then pass on to the physics engine so that you know how to resolve that collision. in our context, collision resolution is going to be a lot simpler. We're going to handle something. So for example, if we collide with an asteroid, we want to take damage. If we also want to make sure that the two kind of go in opposite directions. So you will have to calculate the normals, which for a sphere, for a circle collision is very easy. You already have the normals. The point and the direction of the two is the normal of the collision. So circles have other benefits in terms of the simplicity of the algorithm. And same thing with, like, say I'm shooting a bullet to hit an asteroid. I want that asteroid to break apart. So I need to resolve that collision and then know, oh, if I hit it here, maybe it'll rotate more. So you have to kind of think about these things as well. So the collision resolution can be physically accurate. You can have elastic collisions or inelastic collisions. This ultimately has to do with how you resolve it. So you can write your own little mini physics engine. When a bullet hits a thing, it contributes some momentum and maybe add some rotational momentum and inertia as well. Or it could just be random, where these two things just whatever happens. Like, ultimately, this is up to you and what you want to do and how far you want to push it and what your design goals are for your project and so on. So collision resolution is a whole thing. We're not talking about building a full physics engine here, but there's a lot of fun stuff you can do once you have that data, once you know two objects are colliding in this particular way. Then you can do a lot of really interesting and fun things with that information, such as making an asteroids game, or scaled up, you can do things like building Halo, where you throw a grenade and boxes go flying everywhere. The techniques that those games use is not so far removed from what we've talked about in this lecture. Definitely more optimized, more developed, more honed in, and more sophisticated in terms of the kinds of geometries and the kinds of algorithms that are being used to detect them. But broken all the way down to kind of the base level, it's not that much different. And so, yeah, again, this is why this is such a big interest topic for me. I really love this stuff. There are some pretty crazy algorithms out there, such as VClip and GJK, things like the expanding polytope algorithm to determine your resolution of position of locations, and the really kind of cool stuff. So recommend you guys dig into it more if you'd like, and hope that this is valuable for you to work on your asteroids project that you're working on currently. To talk a little bit about exercise 6, please follow the instructions on my courses. You will basically be conducting a few simple collision tests using the axis line bounding boxes and bounding circle collision detection. Also, to talk a little bit about the midterm, I know there's been a bunch of questions about this, so let me kind of address it. The midterm will be on the 15th. It will be an online thing, kind of like a quiz. You'll have 50 minutes. It'll be written only, no practical, and it'll cover sort of the cumulative topics as listed here. So yeah, please, if you have any questions, hit me up on office hours or on the Discord during my office hours or whatever else. And apologies to everybody in the class for the delay in today's lecture and this week's lecture, and also the quiz 5 confusion. If anybody's watching this that hasn't already gotten wind, just email it to me and I'll deal with it. Great. Thank you for watching, and happy trails.